Okay, I'm going to talk about the work that has been done in N-body during the last couple of years, or maybe 3 or 4 years, in the direction of being able to integrate numerically, collisionally systems in the presence of massive black holes in dense stellar systems, so in galactic nuclei and global clusters. So this work has been done in collaboration with several people in Heidelberg, where I'm finishing my PhD thesis, like Ingo Berenson, Peter Bursik, and Heiner Sturzen. And we also have the external collaborators like Pau, Gabor Kupi, and Gopakumar from Vienna, who helps us with the PN dynamics and gives us input from the relativistic dynamics. Okay, so what's the motivation for us to consider PN dynamics in stellar systems? Well, many of these problems have been taught here and described during this week. So I'll just briefly summarize them. So there are the massive black hole binaries and last parsec problem, where we are reaching the stage where the gravitational radiation might start to be important and affect the dynamics. There are other situations like triple black hole interactions in several contexts, in galactic nuclei or in global clusters, for example. And we are interested in studying carefully, for example, quasi-cycles and the effect that PN dynamics might have on the resonances. Also EMRIs, we would like to try to estimate numerically event rates and be able to try to numerically study resonant relaxation, for example, and also the study of compact binaries and global clusters. So there are a set of problems that examples that we want to deal with. But okay, so the first here, this is an example of a calculation that we've been able to follow for relaxation timescale, a collisional stellar system, dense stellar system, in N-body, and compare it with the Fokker-Planck predictions, which were done by Bacall and Wolf already in 1976. This was possible to do only recently, since these N-body calculations can only be done if we if you use special purpose hardware to speed up the calculations, and this calculation may take weeks or months, even with special purpose hardware. So they are very expensive. Here, so I have to. So the prediction situation is that we have a spherical stellar system with a massive black hole in the center, and we start with a steady state solution of the collision-Boltzmann equation, which has a small cusp in the center in density of around -1/2. And there is the prediction then is that under two-body relaxation, the density cusp will form a steady state solution will be reached where a density cusp of -7/4 within the radius of influence of the black hole, that is the region where the black hole dominates the potential, is created. And so here we see, and this happens roughly on a relaxation time scale, relaxation time scale computed at the radius of influence of the black hole. And we see that now it's possible to observe this result in n-body, reproducing the Fokker-Planck prediction categories well. And also we can see also the distribution function in energy, which is also reproduced and confirms Bacall and Wolf prediction. Now this has been now done by other people as well. Pau Amaro and other groups have been able to do all of these calculations with independent codes. Also multi-bus calculations have been done, for example, by Pau and Mark Freitag and Baumgart and Makino, and we have already done a set of calculations with multi-mass components as well, and with rotation, so with rotating models. Then the other class of problems is as already mentioned before, the binary black hole problem and the last parsec problem, basically. So the idea is, as already mentioned, the black holes after a merger will spiral in towards the center of the galaxy with numerical friction. Once they are bound, they harden due to ejection of stars, and they will decrease their semi-major axis until at some point, once the loss cone, which is a region in angular momentum, it's depleted. So all stars with small angular momentum, such that they can reach close to the binary, are all ejected. The hardening rate or the progressive approach of the black hole stalls. Now, this is the problem that if this happens on a time at a large separation where the time for in spiral due to GR is too long, then they will just stall and won't merge. But these predictions, which were done by many people, for example, Milosevic and Merritt, were made for very idealized models, spherical models of galaxies, and so it's important to study other situations where you take some more realism, like considering axisymmetry and rotation of the stellar model. And this is here an example of a calculation where done by actually this one by Peter Bursick and al., where two black holes are placed inside axisymmetric rotating model, and then and there is an developed an instability on the solar system, which develops a stronger triaxiality, and the black holes just approach each other along this bar, and became bound at very high eccentricities. Now this is an extreme case, so this is a King model with a high rotation, and other situations where the triaxiality is not so strong also will show very interesting results. And here you can see basically this in these two plots. So on this plot on the top, you see the result. This is the result of the hardening rate, so 1 over A evolving on time over semi-major axis on a spherical model with no rotation. And you see that there is a dependence, a strong dependence on n due to the total number of particles. So the evolution is proportional to time over n. And the reason is that you have this empty loss cone, and the replenishing of stars to the loss cone for the black hole to eject them is dominated by diffusive process, and this diffusive process happens on a relaxation time scale, which is roughly proportional with n. That's the dependence on n. But when you go to the case where you have these rotating models, you're falling in the you can observe basically that you don't have a dependence on n, or a very weak dependence on n. So you're already between 200,000 particles, 400,000 particles, because you almost don't distinguish the hardening rate one from the other. And so this indicates there is a full loss cone, and stars are continuously being replenished to the loss cone and to the binary black hole to be ejected. And this can be well understood because as long as you have some triaxiality in the models that's developed, in the case of the bar it's very strong, in other cases it's not so strong, but you always develop some triaxiality. Of course, the angular momentum is not conserved, and so the stars can continuously approach the binary black hole very closely, and so they continue to eject. The binary is able to continuously eject stars. And also another interesting feature is the fact that the eccentricity in these rotating models is actually much higher than usually one observes in spherical models. This is interesting because, of course, the time for inspiral due to GR effects are a strong function of eccentricity, and so if your model, if actually in your model and in nature, the binaries get a very high eccentricity, then that's actually a very interesting effect. And actually, I'm sorry that you cannot actually see this very well here, but there is here a yellow line which corresponds to the highly rotating model, but which shows that the eccentricity is well very high, close to 1. And so this means that at this point we are reaching the point where we want really to have the PN dynamics and study it carefully with this binary black hole problem. So right now we have already calculations running in the cluster in Heidelberg with this PN implementation included to check to study its effect, and also we are doing the calculations in a more realistic way, in such a way that we start in this model. Maybe I forgot to mention the black holes start in one galaxy. In this case, we're trying already to have 2 galaxies from the beginning and letting them merge. Okay, now the PN equations of motion. And these are, as you can see, very large, many terms. These actually are. This is the formulation by Blanchet. This is in harmonic coordinates, harmonic gauge, and this is written for the relative motion of two bodies. There is also, of course, a version with for 2 bodies instead of just this one. We actually tested it and implemented several times. Here we are highlighting the terms that we are including right now in our calculation. So these are basically the 1 PN proportion to 1 over c squared, the 2 PN proportion to 1 over c to the 4th, and 2.5 PN proportion to 1 to c to the 5th power. We still didn't include 3 PN and 3.5 PN. Now, we integrate the sequences of motion with several different integrators. One of the integrators is the Hermite scheme, which is a 4th order predictor corrector scheme, which requires the computation of the derivative of the acceleration, which I call A dot. This will require, of course, that we take the derivatives of this term. And if we want to include this one, do as well. So maybe this will turn out into 4 pages. Which, I mean, which it's by itself doesn't say anything, but from numerical point of view is a problem. Because you have to guarantee that you integrate it correctly and accurately. And this is not so trivial. Now, so we want. I mean, now many people, several calculations that have been done in the literature in astrophysics have been done neglecting the 1 and 2 PN terms and using only the 2.5 PN terms because they are 2.5 is dissipative, so it's a secular effect, whereas 1 and 2 PN are just quasi-periodic. So the assumption is that somehow you could average it out and just consider the secular effect. But I mean, this can be questionable in many, I imagine, situations, like, say, for example, quasi-resonances, where in some situations you might have quasi-resonances if you don't include 1 and 2 PN, but if you include 1 and 2 PN, they might destroy, due to the other oscillations, they might destroy the phase relations that enter into the resonance. And this is actually a plot that was originally made by Gabor Kupi, just to check and with several different codes the integrated the effects of the integrating the equations of motion only up to 1 PN and no dissipative terms, here with 1 and 2 PN, and then with 1, 2, and 2.5. And here in this case only Newtonian and 2.5. The basic idea is just that we did a series of tests like this with several different codes to check if everything was working fine, and we basically get results that agree with each other. But we can see that there is difference in times of merger if you consider or not consider the 1 and 2 PN terms. Now, in all calculations in cell dynamics, we want to check if energy is well conserved. It's a basic thing that we want to do. And here we have the energy. And so, if you neglect the dissipative terms like 2.5, you have you're supposed to have a conserved energy. That even by this expression, here you have the Newtonian. And you have the PN1 term, you have 2 PN, and this is due to 3 PN. Now the question is, is this really conserved? I mean, this is not exactly conserved in the calculation. And so this creates a slight, due to truncation of the series, because as far as we can understand, as far as we understand, this should be conserved if you have all terms, but if you truncate the series, you don't conserve it. So it's a slight problem for us to test the accuracy of the calculation. So we just wanted to do several tests to check if we could get correctly the equations of motion. And so this here is an example where we were looking for circular orbits with using 1 PN terms. And so but the point is that we should start with the Kepler initial conditions. Of course, you get these highly known circular orbits, which have high eccentricities, that's Perset, etc. And actually, this is done for C equals 3, which means that you are artificially increasing the strength of the perturbation of the PN terms. And so we can actually look for initial conditions for circular orbits, and we can do that by using the equations of motion and solving, imposing that R equals 0 is a constant and the frequency is constant, and you can solve for the frequency, and you get this expression for the circular frequency, which gives you a circular orbit. If you use the results from the literature, for example, due to the fact that you're here truncating only at 1 PN, you get an orbit which is not actually quite circular. But this is due to the fact that we're using very strong perturbation, so our parameter Gm over R naught C square is not a very small parameter. Once you make it small, you can totally expand this exact expression and get the expressions that appear in the literature. So And this just shows the differences that happen in for the circular frequency in this artificial case, where you have the Newtonian frequency, usual behavior, and then you have we compare the PN0 exact expression, Taylor expansion from the expansions, and PN2 as well. And you see that these are already PN2 are approaching each other here, and if we go for a very large radius where the perturbations become smaller, they will all fall on each other. And if you go to 3PN, the exact frequencies and the exponent frequencies also become very, very close. So they are converging. And so everything is working fine in the integration. We can reproduce what we want to do in integration. This is just another case. And then we can also do another very simple test that we can do for our calculations is just make a linear stability analysis for circular orbits. You basically write the equations in polar coordinates, consider small perturbations, take the derivatives, look for eigenvalues, and you want that this quantity that is here for the eigenvalue inside the square root, of course, to be negative, the whole quantity to be positive, and this to be negative, so that you don't have, so that the perturbations will just oscillate very stable around the circular orbit, the circular solution, instead of just spiraling in or out. And if we plot the stability parameter against the separation of the black holes, in this case, equal mass black holes and C equals 3 again, you see that you have negative values for all this range, which means that orbits are stable. And when you get to this point, the quantity becomes positive and the orbit becomes unstable. And we can, against this prediction, we can test our integrations, and they actually reproduce this result, which is nice. This actually was done using the exact expressions for circular frequency instead of the ones used in the literature, but this is just for another case. And so, I mean, there is what we want to say here is that we have been testing very as thoroughly as we can these integrations, all integrators with these PN terms. And we would be happy if someone has suggestions of other ways we can test with our calculations, or some interesting configurations to study. As I said, we have calculations right now running in Heidelberg in the cluster, but we still have no ready results to show of the big production runs. So as a summary, this is basically, so we are already studying the binary black hole plotter with PN terms, PN corrections. This is being done Heidelberg, I think in Potsdam as well. This is implemented, it's tested, although we think we have still space for improvements in accuracy and efficiency of numerical integrators. Very important phenomenon right now, as we heard this week, is the resonance relaxation, and we would like very much to try to do the calculations, endpoint calculations to test the predictions. It's a difficult problem, of course. You need very high, around 10 million particles. To be realistic, you need to integrate from many orbits. You need greater accuracy, and you have very expensive calculations. These will be. But we think we can do, if we use the whole cluster, calculations with 1-4 million particles. They should be feasible right now. Also, the MRIs, we'd like very much to study it numerically. But this is actually a very big challenge numerically, even more challenging. You need very high integrate very high eccentric orbits for many periods with PN dynamics, or, well, we'll do it without it as well, but it would be nice to include PN. And you would have very large mass ratio. And this is actually a big problem. One of the standard integrators used is a chain integrator. But the chain integrator is not well suited for very large ratios, very large mass ratios. The chain integrator is basically an integrator that regularizes the interactions using KS regularization scheme, which transforms the equations of motion from the singular Keplerian potential into a harmonic oscillator. And then the chain basically connects several particles, making them being integrated with this regularization scheme. Now the problem is that this is done in the Hamiltonian as an extended phase space, which includes the energy, the total energy. And the problem is that if you have very large mass ratios, the total energy errors, relative energy errors, might be of the size of the energy of the small particle. And so it might mean that the integration of small particles is meaningless. So we need to look for other algorithms, other integrators to deal with this problem. Maybe algorithm regularization. There are some codes that are able to integrate exactly Kuiper orbits with some errant phase, but they integrate exactly the Kuiper orbits. The problem is to be able to include them in n-body calculations. It's not trivial, but maybe it can be done. Also, new other symplectic methods or time reversal methods might help. And also, okay, we are going to starting calculations with compact managed global clusters. This is a situation where our codes are ultimately suited to. And so, as I said, if you have any suggestions for how we should test our PN dynamics and problems configuration that would be of interest, since we rely on relativists to guide us when we are dealing with PN dynamics, we'd be happy to seek suggestions and questions. Okay, thank you. Well, we will, I mean, our plan is to start with moderate number of particles. So, and then keep increasing and see if there is an independence on the results, for example. Might be that there is no independence and that's enough. But if you want basically to accurately model a galactic nuclei or zone of influence of a black hole, you need that order of and also, I mean, you need, if the mass ratio between the particles and the black hole is not small enough, then you have also motions of one ring of black hole, although that might, black hole transports the curve, that is not such a problem. But. Okay.